Kudos to Wake Tech for loading Edge or Chrome to this laptop. All right, what questions you got for me? According to Abby, according to the website, there's about 7 other people right now. So I don't know who else is online, though. Let's see if I can figure it out. Actually, no, it's just you and me right now. Oh. Got a few other people. All right, so we'll start with Abby. Abby, you had a few questions. What were they? Okay, so discussion board charts. So when I first started teaching Chem 2, I had a student, and this is where the blur diagrams came from. We're trying to explain to him how to convert between pH, POH, H plus, and OH minus, because he just wasn't getting it. So there's 4 terms. pH, POH, concentration of H plus, concentration of hydroxide, OH minus. So how do we convert between the two? Well, this is just a formula. If we go from H plus to pH, all we do is take the negative log concentration of H plus. And the reason it's set up this way is that it's basically the same thing up here that it is down here. So to go from OH minus to POH, it's just the negative log concentration of OH minus. To go back, our concentration of H plus is 10 to the minus pH, and similarly to go back to the OH minus concentration, the concentration of OH minus is 10 to the minus POH. So that's where the first part of this diagram comes from. These are just mathematical definitions. P is defined as the negative base 10 log of any number. So the diagram here is meant to emphasize that the go between these two numbers, the concentrations and their P values, it's the same formula. Now the connection between these two is Kw. So Kw is the concentration of H plus times OH minus. Over here, relationship is that 14 equals the pH plus the POH. Ten to the negative pH. The reason we're using 10 to the negative pH is that P is defined as the negative log of a number. So P is actually a mathematical operator. So when we say we're taking pH, we are taking the negative log of the H concentration. Now, I think I have proof in the notes for where this 14 equals pH plus POH comes from, and the Kw, where this comes from. This is Kw just equals Q, and you're doing Q of this reaction, H2O going back and forth to H plus and OH minus. Now, the other reason this diagram exists, there is no way to go directly from H plus to POH or pH to OH minus. But there are 2 other ways. So even though you can't do it directly, you can go from here to here to here, or from here to here to here. So it's meant to kind of give you a flow diagram on how to convert from one number to the other. Last part of the discussion board. Let's bring up the discussion board and find out. So it's asking you what is the pH of the concentration of the H plus is 10 to the negative 7. So let me create a little bit of space on the whiteboard. So we had a relationship if we had from the Blair diagram. To go from H plus to pH, we just take the negative log, the concentration of H plus. So in this case, it's the negative log of 1 times 10 to the negative 7. Now this was meant to be a really easy problem. The negative log of 10 to the negative 7 is just simply saying what number do we have to raise 10 to get 10 to the negative 7. So in this case, it's negative 7. So our pH is 7 if the concentration of H plus is 10 to the negative 7. All right, other questions? Section 14.5, polyprotic acids. They did an example with two-step ionization processes. The first ionization used an IC table, but the second did not use an IC table. So off the top of my head, I don't know what they did in the book. I know with most weak acids or polyprotic acids, typically the first ionization constant is so much larger than the second that if we have the first proton there. So let me give an example here. So let's say we have a weak diprotic acid like H2SO3, sulfurous acid. And really what's going on in the solution is we have two dissociations. So typically when we look at these diprotic dissociations and triprotics, if we've got the H2SO3, we're going to ignore the deprotonation of the HSO3 minus. And if we've only got the HSO3 minus, we're not going to worry about the first equilibrium. The reason being is that the Ka for this one, so Ka1 versus Ka2, is so much larger, we can effectively pretend that the second reaction isn't actually going on. Now, that said, if you wanted to solve it for both of them, the complication is that you're actually going to have two extensive reactions, X1 and X2. So when you set up your IC table, for example, when you have H plus is actually X1 plus X2. So if you just had the H2SO3, the amount of H2SO3 would be X1, the amount of SO3 minus 2 would be X2. These basically just become very hard algebra problems. So as a first pass approximation, we just typically ignore it. So we don't care about the second dissociations. If we had something like phosphorus acid, H3PO3, we would ignore the third dissociation. Don't know if that answers your question. My guess is they didn't show in the IC table because it's just impossible to solve for a diprotic going on with solve for both dissociations of a diprotic. Is this in the study guide? Yes, we talk about the definitions of mono, di, and triprotic acids, but as far as you solving an IC table for like 2 dissociations or 3, that's not going to be on there because that's just impossible to do by hand. So basically, after the first ionization process, we basically consider the reaction done. So when we calculate concentrations, we treat the concentration from the first calculation as it being done. Correct. There is some further dissociation, but it's like 1,000 times smaller, so we just ignore it. Yeah, we start working through the study guide. Okay, so you want to work through the study guide. Let's talk about, well, which sections do you want to focus on? So you mean like the first page? work through all of them. So let's start on the first page then. So the basic concepts, strong acids versus weak acids. Just out of curiosity for those of you who are on here, do you know the difference between a strong acid and a weak acid? Oh, Elijah's already asking that. So if we look at a strong acid like HCl, this is the reaction. So if you look at a weak acid, so what's the difference? And everything I have written there is correct. Looking too far on the reaction, what's the difference between the two reactions? Not just the compounds. So the compounds are inconsequential. What do you notice about the reactions themselves? You write bigger. Let's see if I can move the camera closer. Of course, now I can't see the chat window. There you go. Elijah got it, so did Abby. The thing here is, so your weak acids and bases are reversible, whereas your strong acids and bases are not. So the way we distinguish a weak acid from a strong acid is a strong acid irreversibly dissociates in water, whereas a weak acid or weak base does reversibly dissociate. So there's some of this parent ion in there. Now, as far as knowing which one's which, there's actually a very easy way to do this. Memorize all the strong acids and the strong bases. And everything that is not a strong acid or not a strong base is a weak acid or weak base by basically default. So in terms of the strong acids, there's a list on the course website. Are actually the only hard ones to memorize. HCl hydrochloric, HBr hydrobromic, HI hydroiodic, HCl4 perchloric, nitric acid HNO3, and sulfuric acid H2SO4. Now this, for H2SO4, it's only the first hydrogen that's strongly acidic. The second one's actually weakly acidic. The strong bases, these are the easiest ones to memorize. If you go to the periodic table, the first two columns, so hydrogen, lithium, sodium, potassium, rubidium, cesium. The second column, beryllium, magnesium, calcium, strontium, barium. If you look at the first two columns, the second elements down are all strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. Those are all strong bases. Everything else is a weak acid or a weak base. Yeah, I mean, that's pretty much it. Just memorize what the strong ones are, and everything that isn't strong is weak by default. Okay, so it depends. These are going to be acidic and basic salts. I don't think we would quite be to that point in this semester. We can talk about it. So in order to figure out if something is a weak acid, an acidic salt, a basic salt, or it depends, we have to look at the salt itself. So let's consider three salts: sodium chloride, sodium carbonate, ammonium chloride, and ammonium carbonate. So this one is neutral. This one's basic. This one's acidic. And this one depends. And what it depends on is the relative acidity and basicity of ammonium and carbonate. So how would you know, looking at this, what they do? Well, every salt is composed of a cation and an anion. So let's make our generic salts. Erase one of these off. Make our salt AXCY. And I know C is an element, but we need an anion and we need a cation. So our anion is going to have some negative charge, and our cation is going to have some positive charge associated with it. So if we look at water, yeah, still setting up the whiteboard. So water is going to break into two ions, H2O, or H plus, and OH minus. So the question is, do the anions and the cations react with the water? So the anion is negative. What do you expect it to react with, the H plus or the OH minus? Yes, but you know I bounce around on the study guides, so it doesn't matter where it comes sequentially in the book, in the study guides. There you go. So if the anion is going to react, it's typically going to react with the H plus to give us HA, and what remains of the water is the OH minus. So the way we would write this is that the A minus plus the water goes back and forth to HA plus OH minus. So if the anion reacts with the water, it's going to take out an H plus and leaves with hydroxide. The cation, if it reacts with water, is going to react with the OH group and leave us behind with an H plus. So what we have to do is we have to figure out if this reaction occurs. And the trick here is what's formed. So HA is an acid, COH is a base. If these are strong acids and strong bases, so let's say we form HCl and LiOH, this can't happen. And it can't happen because bases don't participate in reversible acid-base reactions. They are irreversible because they are strong. So if the anion forms a strong acid, it doesn't react. If the cation forms a strong base, it doesn't react. And if it doesn't react, it doesn't affect the pH. So if we go back to something like sodium chloride, sodium here would form sodium hydroxide, Cl would form HCl. And so since sodium hydroxide and HCl are both strong ions, we would say neither of them occur, so neither one is creating OH minus or H plus, so this ends up being neutral. In the case of sodium carbonate, you get NaOH and HCO3. We're only going to consider the first hydrogen and the first hydroxide. So bicarbonate's not a strong acid. Bicarbonate's not a strong acid, but sodium hydroxide is. So in the case of sodium carbonate, the anion doesn't react, but the cation does. I'm sorry, other way. The cation doesn't react, but the anion, the CO3, does. And because it does, we end up forming OH minus, which would make this a base. Now, ammonium's kind of a weird one, and I listed as one of the exceptions. Cl here is going to form HCl. If you see ammonium, ammonium is acidic. It forms NH4 plus, which dissociates to give you NH3 plus H plus. So this component here is acidic. Now, the reason why NH4 CO3 depends is that this produces H plus, which is acidic. This creates hydroxide, which is OH minus, which is basic. The question is, who's better at their job? Is ammonium better at giving up hydrogen, or is carbonate better at accepting it? And that's where that it depends statement comes from. Actually trying to work right now with the faculty when we come back. We're going to try to create a lab where you actually go through and measure salts and try to figure out these rules on your own, since we don't really have a buffer lab and we don't really have a lab that teaches you this concept. And it is kind of abstract seeing it up here. Even when I teach it in class, it takes a long time for this concept to sink in. I agree. Well, a buffer lab would also be good. Oddly, the concept of buffers is qualitatively not that hard, but students don't get it, which is weird because y'all can do the math all day long and give me the pH, but so many of you struggle to tell me what's actually a buffer. So it would be nice to actually have hands-on demonstrations of these more abstract concepts. So let's see what page 2 is. Oh, good. It actually talks about buffers. So page 2 is historically a page where students have struggled. And again, it's because the rest of this packet you probably won't struggle with, but this section here will just really create issues. Why is carbonate a basic indicator? I've never heard it called a basic indicator before, so I'm not sure what that means. It's not really related to which of these is a buffer. So there are 2 requirements for something to be a buffer. Okay, first of all, we'll back up. There's 2 types of buffers: acidic buffers and basic buffers. So just out of curiosity, those of you online, what do you think the difference between acidic buffer is versus a basic buffer? Isaac, I wonder if by a basic indicator, I know carbonate will react with acidic solutions to form CO2, so it may be a basic buffer because it doesn't react in buffers in basic conditions, but under acidic conditions, it forms CO2, which is really obvious that you're underneath acidic conditions. And actually, it's a good test to see if you've neutralized the solution. Just keep adding sodium bicarbonate until it stops fizzing. So back to the question at hand, what's the difference between an acidic buffer and a basic buffer? And actually, it's a pretty straightforward answer. Try not to overthink it. Simpler than that, Elijah. Actually, an acidic buffer is just a buffer that has an acidic pH. And a basic buffer is something that has a basic pH. So there are properties of buffers, and then there are what are actually considered buffer solutions. So a property of buffers is that they resist pH change. The idea is that if you add acid to an acidic buffer or a base to a acidic buffer, it's going to kind of keep the pH in a very narrow range. So this is true of your blood. Your blood is a weakly basic buffer. It tries to keep the pH right around 7. It takes a lot to shift the pH of your blood. Sort of. They just have a really good. So Elijah asks, oh, so they cancel the other out, basically. It's more that because it's a weak acid, there's always some acid on reserve. And because the weak acid associates into a conjugate base, there's always some conjugate base in reserve. So you have both acid and base present in the reaction, so it can absorb the acid or the base depending on where it is. And Le Chatelier's principle is going to say that when you start adding a base equilibrium, and the equilibrium is going to hover right around where you expect the pH to be. So there are 2 things we have to have in order to have a buffer. So with the acidic, we have the acidic buffer. For a basic buffer, and typically our basic buffers, we're going to be working with the Bronsted definitions. The two things that have to be present is, one, we have to have a weak. So for the acidic buffers and reversible reactions, so we're also going to have the conjugate. So for us to have a buffer solution, there has to be a weak acid with its conjugate base or a weak base with its conjugate acid. And the idea here is that because it's reversible, because it's an equilibrium, if we add an acid to this, it'll go backwards to try to get back to the pH it was at. If we add an acid to this, it will go forward to try to get rid of the acid to get back to the conditions it was at. And the reverse is true. If we add a base, we remove the H+, more of the acid will dissociate to try to keep us at pH. If we add a base, this will go backwards to try and keep us at the pH we were at. So that is the definition of a buffer. A buffer is a weak acid with its conjugate acid or a weak base with its conjugate base. You have to have both, and you have to have weaks. So basically, if you have nitrous acid, HNO2, you need something that will dissolve with NO2. And that's all that first part of the test is at. First part of that page is asking you is, can you identify which of those would form a good soluble complex of NO2? Some of the other examples, which of the following are buffers? It's basically asking you, well, okay, where's the conjugate acid? H2SO3 going back and forth to H2SO minus and H2 plus. So Elijah's asked, how do you identify the conjugate acid and the conjugate base? So if we have an acid-base reaction, we're going to have both. We're going to have an acid and a base. So everything on the left of the arrow is going to be the acid or the base. Now the acid, we're probably going to stick to the Arrhenius and Bronsted definitions at this level of chemistry. If you go for organic, that's when the lowest definitions start showing up a lot. But by the Arrhenius and Bronsted definition, the acid is whatever loses a hydrogen. So the H2SO3 goes to HSO3 minus 1. That makes this the acid. Since it's reacting water here, is going to be the base. It's going to be the proton acceptor. The conjugates appear on the right side. So we say conjugate acid, conjugate base. RIP, the organic students having to do this online. Actually, it's not as bad because we don't actually have any labs for them to make up, so it's nothing but discussion boards for them this semester. You guys actually have to do labs, so they got a little bit easier than you. So on the opposite side are the conjugates. The conjugate base is whatever the acid became. So we have H2SO3, it loses a hydrogen. So this is the conjugate base. The base, when it accepts a hydrogen, going the reverse way is going to act like an acid. So this becomes the conjugate acid. So we identify the conjugates. Conjugates are going to be on the right side of the reaction. The conjugate is the opposite of whatever it started as. So since H2S3 started as an acid, its conjugate is a base. Since water starts as a base, its conjugate is going to be an acid. And we get that definition by looking at how it acts in the reverse direction. Going to the left, H3O plus loses a hydrogen to become H2O, so it acts like an acid. HSO3 minus 1 accepts a hydrogen from the water to give you HSO3, which makes it a base. The overarching arrow here is showing you that H2SO3 becomes HSO3 minus 1. So that's how you connect the conjugates to what they start with, is you just look at what sort of looks like that compound to begin with. That's what you use to determine the conjugate. Pretty much, yeah. You look at the left side and see what everything became. So try to easiest thing is to figure out what became an acid, because acids are the easiest to identify. You lose a hydrogen. So H2SO3 loses a hydrogen, become HSO3 minus. This is an acid, therefore it forms a conjugate base. Correct. So to figure out what the conjugate is, you figure out what the acid became. So what did it become after it lost a hydrogen? And conversely, to figure out what the conjugate acid is, look at the base and see what accepted a hydrogen to become a base. Charges are less reliable in this case. You can kind of think of it that way because the hydrogen is an H+, but if you look at something like NH4+, actually, I'll write that out for you. So if you look at ammonium, ammonium starts with a positive charge. It loses a hydrogen, so it acts like an acid to form ammonia, NH3, which is its conjugate base. Water starts out as H2O, becomes H3O+. So I hesitate to tell you to follow the charges because the charges can be misleading. You can definitely have positives and negatives in there. But if it helps you, anything that becomes more positive on the right side, it had to react with a base. Anything that becomes less positive acted like an acid. Yeah, Abby, I'm trying to do the poor man's whiteboard. So this is actually a cover for a fluorescent light. And I'm thinking I'm actually going to get the contact paper to put on top of it, but it has worked pretty well. It's just getting to the point that you can only put so much rubbing alcohol on it before it stops not absorbing the ink. Now, they did give me a whiteboard to take home. Unfortunately, this is as big as it is. I need a little bit more space than that. Yeah, I got it for free from the school, but if I had like stolen 2 or 3, I might actually have enough to like write on this wall. It was cheaper than the alternatives, which was like 50 or 60 bucks for like a slightly larger whiteboard. This was like $15 at Home Depot. And I got in there before they made a standing queue. Page number 5. Yeah. So page number 5 is basically just conversion problems. Let's see if I can split this up with a video. Oh, this laptop's awful. What is the pH at the concentration of H+? Oh, clean the board off real quick. So the problem starting pH at the concentration of H+ is just 0.00457. So to figure out the pH, we just take the negative log of that number. And that's it. You just plug into your calculator and you will get a number back out. We'll be uploading the stream. Yeah, actually, this is going to be posted to my YouTube channel when I finish. And when I get enough of them compiled, I'll actually create a playlist for this test. Mostly, I want to see how well this went today. Learned a lot of things, like you can't possibly do this on Microsoft Edge. So I was a few minutes late signing in. Yeah, Blackboard's not the best for uploading figures. As you probably noticed, your test, some of your figures were really big. Some of them were very small. No idea what was controlling that effect. Correct, Abby. So if you want to figure out the POH, let's say you were given the concentration of OH minus 0.00457. The pH is just the negative log 0.00457. So I think when you get this, you end up getting like 2.34 or something like that. Yes, Abby, it's actually pretty easy. That's why I give you that flow diagram. Problem from page 7. Okay, so this is where we actually start getting into the heart of pH problems. Now, the speech I usually give when I'm in the classroom talking about this is that you actually know how to solve all these problems. They're actually very easy problems from test 2. So if you go look at the test 3 packets, there were several weak acid examples that worked. But we didn't put any pH associated with them. So when we solve any equilibrium problem, there's always 3 things we need. We need the KQ, we need the IC table, we need the expression for Q. Now, because we're always working with weak acids and weak bases, the reaction is very simple. In this case, we have HF going back and forth to H plus and F minus. And as was the case for the test 3 packets, the reason we had that sodium in the problem, but we don't see it up here, is the sodium is just a spectator ion. So we've got a reaction. We've got Q, concentration of H plus, concentration of F minus, all the concentration of HF. And this is going to equal our equilibrium constant, in this case, Ka. Now, what you're given is pKa. The reason this is given to you in tables, it's a lot easier to write. So to go from pKa back to Ka is the same relationship we're going from pH to H plus. Ka is just 10 to the negative pKa. Now, the other thing we need to solve any equilibrium problem is we need our IC table. So we got HA, H plus, and A minus. Now, the initial concentrations are given to you. You're given 0.5 molar HF, 0.25 molar sodium fluoride. And in this case, we're going to assume, even though water has H plus in it, we're going to assume that the concentration is effectively 0 compared to what the acid is producing. Our changes, minus X, X, and X. So we get 0.5 minus X, 0.5 plus X. Now, the problem here is asking you to find the pH. Well, the pH is just the negative log of the concentration. So all we have to do is just find this number and take the negative log of it. So plug this in here. We get X times 0.25 plus X over 0.5 minus X equals Ka. The nice thing about acid-base problems is because typically our H plus and OH minus are going to start with 0 concentration, so our N value is always the extent of reaction. We're only going to take the positive. So if you work it out, you get that X is the opposite of Ka plus 0.25 plus the square root Ka plus 0.25 squared plus 4 Ka times the starting concentration all over 2. And then you would just take the negative log of that number. So you've actually solved a lot of these types of problems already. The big difference here is that we're no longer just solving for what's in this table. We may be doing things with what's in this table. So if you're asked to find the pH, you're going to solve it like a normal equilibrium problem. And then when you find your concentration of H plus, just take the negative log of it. Now, I will give you fair warning on the next exam. You are expected to be able to write out the acid or the base reaction. If you're given a Ka, it's an acid reaction. If you're given a Kb, it's a basic reaction. There is a lot written underneath here. So it's K plus 0.25 quantity squared plus 4 Ka times the starting concentration 0.5. Actually, if you go into the notes, I give you a generalized solution for this. I don't want to erase what's written up here. Basically, the generalized solution, there's a formula for it. And then down the road, we'll talk about the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation does these faster, but there's assumptions built into it that you need to be aware of. In this problem, the Ka is actually 10 to the negative 3.18. So pKa and Ka had the same relationship as pH and H plus concentration. To undo the pK, it's 10 to the negative Pa will give you Ka. And that's a very common mistake I see students make. So Kb is solved in a very similar fashion. Instead of having an acid reaction, you're going to have a base reaction where it accepts the H plus, and instead of forming H plus, it's going to form OH minus. But the approach is the exact same. Set up your IC table, set up your expression for Q, plug in the variables. It's going to be the positive root because you're going to end up having extended reaction by itself for the OH minus concentration. Once you know OH minus, you've got that Blair diagram that we talked about at the beginning to go from OH minus to POH to pH, or to go from OH minus to H plus to pH. So how do you write out the equation? So the problem I'm going to look at, by the way, we typically would not be this fast in the start of the semester. But if you go to page 12 in the packets, typically we talk about bases towards the end of this unit. So let's say we're working with ammonia, and ammonia acts like a base. Almost always for the basic problems, we're going to do page 9, the last problem. Give me just a minute. So we'll come back to that one. Talk about basic reactions really quick. So the first, sorry. So if we have a base, they're going to accept the hydrogen and OH minus. You can derive the IC table, and you'll be given a pKb. I'm not one of the professors that'll give you a pKa and say, oh, now convert to a pKb. That's too many steps. If you're given a pKb, I'm asking for the basic conditions. So does that answer your question, Elijah, about how you would do KP problems, or do you want me to go a little bit further? Yeah, for now, good. And we can come back later. Typically, we don't do bases towards the ends of this unit because it's, once you get acid base down, bases are very similar. There's a few extra steps. All right. Page 9, last problem. So it says acidic buffer. What makes that a buffer? So it says, what is the pH of an acidic buffer solution that is 0.025 molar HClO2 and 0.05 molar NaCl2? So again, what makes this a buffer problem? And actually, the wording here is actually very precise. First time I taught this course, I had a student point, I was like, well, this is a buffer and this isn't. So this is, there's actually a very precise wording in a lot of these problems. So the question is, it says acidic buffer. What makes this a buffer? Because you'll notice the first problem in this section, it just says an acidic solution. It doesn't say acidic buffer. Here it's saying an acidic buffer. So what makes it a buffer? Specifically, it has the conjugate base. So Isaac had it mostly right. It's a buffer solution because we have the acid, HClO2, and we have its conjugate base, ClO2 minus 1. So we have chlorous acid and chlorite. So to figure out the pH, still build your IC table. So we're going to have that Q equals KQ. So K equals Q, which equals the concentration of H plus, concentration of ClO2 minus 1, all over the concentration of HClO2. And our IC table, HClO, H plus, and Cl2 minus 1. And we have 0.025 and 0.05. So to answer the question that got asked, it makes the reaction neutral. It doesn't make the reaction neutral because overall we're netting an H plus. The H plus is what's the acid in this case. Now, it's a base in the sense that it reacts away the H plus, but it is not a neutral solution because the acid and its conjugate base are there. This would actually be an acidic buffer that has a lower pH than that. So put it this way, there's always H plus and there's always OH minus in water. What makes something acidic or basic are the relative ratios. So what we're learning in here is that there's OH minus in the water as well, but there's a lot more H plus than there is OH minus, which is what makes this an acidic solution. All right, back to solving it. changes, minus x, x, and x. So we get 0.025 minus x, x, and 0.05 plus x. If we plug that in, we get x, 0.050 plus x, all over 0.025 minus x. And because I don't have the space up here to show it for you, you would just use the quadratic formula and get the positive root. Now it's asking you for the pH. The pH is just this square here. So whatever number we get for the extended reaction, we're just going to take the negative log of that number. And that will give us pH. You asked about page 9, Abby, so this is actually the bottom of page 9. Now, the advice I give students with a lot of these problems, make sure your answer makes sense. When you find your pH, it's an acidic solution, so the pH should be less than 7. Yeah, pretty much. I mean, you're going to find when you work on other problems, they're solved the exact same way. So test 3 was equilibrium, but it was a very broad equilibrium. We had to cover every type of equilibrium. This is specifically acid-base equilibrium. So the equilibrium problems themselves are super easy to solve. What makes this test hard is the periphery questions. How do you find the pH? What mass of acid do you need to get this given pH? Things like that. Correct. Well, so the thing with pH is there are no POH probes. There are only pH probes. If we want to know the concentration of OH minus, we have the flow diagrams from earlier. So we can convert from pH to POH to OH minus to H plus concentration. This second reaction of water is still going on. So this is kind of going on in the background. There's still OH minus there, but it's acidic because if we look at the concentration of H plus, it's actually greater than the concentration of OH minus. So that's all an acidic solution is one that has excess H plus. A basic solution has excess OH minus, and a neutral solution has equal ratios of both. Now, typically we work with basic buffers or bases in general. We work with the OH minus and then we back convert into the pH. So we figure out our concentration of OH minus and then go back to pH. So H plus to OH minus, if you go back to that flow diagram, if you're given H plus and you want to go to OH minus, the easiest way is you just take your value for Kw. We have this relationship, Kw equals H plus times OH minus. Concentration of OH minus is Kw divided by the concentration of H plus. And actually, it's a shame. We would prove this relationship in class. I just don't want to do that, particularly when I can't get feedback from you all students. This relationship is actually very easy to see if you look at it based on what you already know. So this is the auto dissociation of water with equilibrium constant Kw. At equilibrium, Kw equals Q, which is this H plus times OH minus. So that's where this relationship comes from. Is it saying that at equilibrium, Q equals KQ, and this is your expression for Q. So for now, I'm going to have a pre-lab and post-lab. So the question here is, we've got the online lab assignments. Are we supposed to do pre-labs and post-labs? For now, and probably for the rest of the semester, I'm going to say no. What I'm weighing right now is how to do the lab notebooks. As instructors, we've been passing around information, trying to figure out what's the best way to do it, because a lot of us have been grading your lab notebooks halfway through the semester. And if we knew we weren't coming back, we would have taken up all your lab notebooks. Odds are what I'm going to make you do at the end of the semester is just take pictures of all my grading marks and then take pictures of all the labs that you've done online. So go ahead and transcribe them into your lab notebook and give me another week or two. We're still kind of debating back and forth about what's the best logistical way to get your lab notebooks to us. Because I'm definitely not giving you my home mailing address to like mail me your lab notebook. I figured some of you would appreciate that comment. What's sweet tea a euphemism for there, Elijah? You're going to submit the lab worksheets through the course website. So there should be a submission link within the makeup folder itself. You just click on it and upload your assignment. To answer your question, Abby, I'm going to break down and actually buy the contact paper as well, so I can put the contact paper on top of this, but it's still better than writing on the wall. This is an improvement over my little word. This is the Chatelier's lab. Hold on, let me check the website for you really quick. Actually, I'm sorry, Malika, it's actually under quizzes and assignments. So what goes into what you're turning in, or what goes into your lab notebook? There are ways to sync it with the lab folders. It creates a mess in terms of internal links and accessing. So for right now, it's just going to be on the quizzes and assignments, and just know that it's there. And if you have questions or you can't find it, just shoot me an email. If it's a legitimate lockout issue, I'll reopen the assignment. Two-post was the original idea. So if you look at a lot of online instructors that require you to do two-post, I'm kind of phasing out that idea. That seemed like a nice idea when people were proposing it, but having done online courses, particularly with Wake Tech, I absolutely detest responding to discussion board posts. So I'm going to back off on that two-post comment. I was still trying to develop what I thought was going to be a good idea at the time. So if there is a response, you only need to respond to one. But the idea with the discussion boards, one is attendance, and just to make sure that you're keeping up with the material. What goes into what you're turning, you're just basically going to fill out, for pretty much all of these, there's a worksheet, and you're just going to fill out the worksheet and submit that. There is one lab, the Ka titration, you're going to go online and you're going to do a print screen, and you're going to submit the print screen from what you did. That's correct, Abby. So download the worksheet off the course website, fill it out, and submit it back. The worksheet, if you go under lab resources and under makeup labs, there's going to be a Le Chatelier's lab. It's in there. It's not that hard a lab. The shame is the Le Chatelier, I wrote part 2, so we actually changed part 2 from the lab manual. It's much better, and we're actually going to change part 1 next semester, so it should be even better. But there are 2 really cool experiments for the Le Chatelier. One where you look at endothermic versus exothermic because you see massive color changes in the compounds. And this is one of the few qualitative labs, so you typically get 100 on this lab. You really have to have something objectively wrong not to do well in this lab. Sure. So I've actually set up the next one. I'm going to update the announcement probably today or tomorrow, so you'll have the copy of the next live stream. And again, once I get like 1 or 2 of these set up, then I'll start the playlist. So this way people can come back to the playlist. But yeah, I agree with you. This seems to be working pretty well. It felt like I was getting kind of lukewarm reception at first, but it's good to know that this is working. Because you might have guessed, like, the big thing for me right now has been setting this up. I've actually got my own audio video equipment versus what the school has loaned me. So what you're not seeing behind here are all my lighting rigs. I've got my tripod. I've got a lot of things that I've had to basically adjust my spare bedroom to be able to do this. Ultimately, what I also want to do is put videos in the announcements as well. But again, the school has not passed me the software I need for this. So a lot of odds and ends going on right now. If they would give me Camtasia, I could do a lot more. Right now, I'm just kind of having to do the videos as is. I refuse to go back to my Movie Maker with Windows. It's just a horrible program. The webcam they provided me is a really nice 1080p webcam. Like, they actually spent good money for it, but my actual video recording rig, I have my own boom microphone. Like, I actually have my own camera, but my camera can't really do live streaming that well. So they've given me some good stuff, but I'm also kind of waiting on some good stuff as well. Yeah, so for the rest of the semester, it's gonna be consistent. You get the assignment at the start when your normal lab period is, and you have a week to complete it. And I think that's pretty fair, particularly since most of these are just online assignments. You're doing them on your own. When you do the lab practical, there's still going to be a lab practical, and I'll send more information out about that. It's an online test. You will have all week to take it. So you'll get 2 hours and 50 minutes. It does not take 2 hours and 50 minutes to take it. Some of you have actually taken it. So there was a lab practical quiz that showed up. I forgot to take it down. That's what you're actually doing. I'll also give you an update. They're still trying to finalize what to do with the final exam. In the air because we don't necessarily have to give a common final like we normally do. So we're discussing as faculty if there's anything we want to do common. What I'm going to do for my final, because this is an option they have given us, you will have all 5 days of finals to take the final. It will be a 2-hour online final. multiple choice to make the grading pretty easy, but there will be partial credit associated with each of the multiple choice answers. But you can take it when you want to. So you will have all 5 days. I think I'm going to put the cap at starting it at 3 o'clock on Friday, just for my own sanity, because the grades are actually due the following Monday. Was that something from the start of the semester? I'm sorry, Isaac, what were you referring to? So actually, it was a debate. So what I really wanted to do this semester was to make you give presentations for the practical. So the practical itself was you physically come in, there are 7 setups, you do each setup on your own, you do the data analysis, and you turn it in. I'm not a huge fan of it. And what I did last summer was that I made students give an oral presentation on one of the previous labs. So each lab group signed up for one of the labs. They gave a 20-minute talk on the labs, and I found those to be a lot better. That said, I still hadn't had approval by the time we got to spring semester to do that. So I had the lab practical quiz up in the event that they were going to tell me no, and you were still going to have to do the lab practical as it is normally done. So it was there. I just forgot to take it down. It's kind of been there from the start of the semester, but again, I was still debating what to do up until a month ago, and then we're in the situation we're in now. So I think early March is when we began to worry about whether or not we'd be shut down, and that's kind of took away from focusing on the lab practical. To answer your question, yeah, it was there, but it was like I was on the fence about what I could do because I hadn't gotten approval yet. All right, so I'm going to stop the live stream. I'm going to send the link out pretty shortly for the Wednesday live stream, since you all see this, and we'll just make this an every day, every week thing. Come with your questions. I'm filling that later. Yeah, I'm going to send out an email down the road. It's too early to worry about the practical right now. I also need to go through, it's a practical quiz that I set up a long time ago. I need to make sure you can still answer the questions that are in there because it was designed for people who've actually done all the labs. But again, I'll send out more details as we get closer. And as instructors, we are trying to be flexible. Like, we understand that a lot of you are kind of having to do this when you can get to it. So definitely there's going to be a lot of communication your way. But anyway, I'm going to shut off the live stream now. I'm going to eventually post a link to the course website, probably link the lessons link at the top of the lesson. So this way you'll have access to all the previous live streams. And yeah, I'll see you all Wednesday.